So doing practice problems with SN1 and SN2 is really the best way to learn these two reactions. And I wrote at the top of this slide that there's 3 things you want to consider each time we're approaching these reactions. You want to look at your leaving group. Is it primary, secondary, or tertiary? And remember that primary and secondary favor SN2, and secondary and tertiary favor SN1. So secondary overlaps, and we need to look at the other factors before we decide. For a nucleophile, we have good or bad. A good nucleophile is required for SN2. A bad nucleophile is SN1. And then we want to look at solvent. So polar protic is SN1. Remember that it contains a OH or a NH. And then polar aprotic is favored for SN2. So we want to think about each of these 3 factors for every reaction that we do. And so in the first reaction, we see that we have our alkyl halide, we have water, and we have heat. Okay, so if we look at our starting substrate, our bromide's attached to a carbon that's attached to 2 other carbons, and so we have a secondary bromide. That means it can go either SN1 or SN2, and so we have to look at the solvent to tell. Our solvent here is water, which has an OH, and so that's polar protic. And polar protic is telling me that I'm going to favor SN1, and the heat also helps with SN1. So these all together tell me that I'm going to have a SN1 reaction. And we don't have to draw the mechanism each time, but I would suggest that you at least consider the carbocation when you're doing an SN1. And so our carbocation is going to form where the leaving group leaves. So remember, the leaving group leaves and our carbocation is going to form right here. And I'm going to put it in brackets. My stereocenter on the left stays. But my stereocenter where my bromide was is gone, because remember that a carbocation is planar. And so my nucleophile can come from either the front face, which is the same as this group, or the back face. And so my nucleophile is water, and water is going to provide me with alcohol groups in my products. So if I draw the backbone, that's still there, and then water provides an alcohol as a product either on the front face, and it can attack from the back face and put my OH on the back. In both cases, the group on the left stays the same. So I get 2 different products here, and the relationship between these 2 are diastereomers, because one stereocenter stayed the same but the other changed. If I look at my byproducts, I have the leftover from a OH is H, and then the Br. So technically HBr, but the strongest acid you can have in water is H3O+, and then Br-. So those are your 2 byproducts. Okay, so this is a SN1 reaction. If I go to the second problem, I want to do the same thinking. I look at my bromide starting in the Fischer projection, and the bromide's attached to carbon that's attached to 2 other carbons, and so I have a secondary leaving group. That's my bromide. And then I look at my nucleophile, and my nucleophile has C triple bond C and the Na, so I'm going to rewrite it. Oops. The Na tells me that I have Na+, and so my carbon must have a negative charge and a lone pair on it, and that was an acetylide. And acetylide is a good nucleophile, which is pointing towards SN2. So then this tells me I could go either way, but this tells me SN2. So these together tell me SN2. And what solvent is best for an SN2 is polar aprotic. Remember that there are 4 to choose from. I can pick any of those 4, and so let me just say DMF, for example. Now when we do an SN2 reaction, we have to keep in mind that we undergo inversion. So how do you show inversion in a Fischer projection? We have not done that type of an example yet in this chapter, but before, when we learned Fischer projections in chapter 5, we said if you flip any two, that's an inversion. So if my leaving group is at the top, then I want my nucleophile at the bottom, and my nucleophile is going to be this portion of the molecule. So C triple bond CH is going to attack from the bottom. It's going to kick my leaving group out, and it's going to at the same time push the H up. And then the other two groups stay the same. And then my byproduct, I have my sodium, and then I have bromide. So sodium bromide. Okay. So remember the inversion changed R and S. So if we sign R and S here, bromine is 1, ethyl versus methyl is 2, 3, 4. I make my circle from 1, 2, 3. In 4, as shown in the Fischer projection, remember if you're vertical, you're a dash, so 4 is in the back. Because 4 is in the back, I can assign my circle as is, which is R. And if I assign that circle here, my alkyne now takes priority. My H is still in the back. And I now have S, which makes sense that I did the inversion for SN2. Okay, so keep in mind for SN2, we have inversion only. For SN1, in our first case, we have retention, because our nucleophile was in the same side, and we have inversion. So you may also have other types of problems that aren't just straight predict the products. Okay, and that's what these next few are going to do to get some of the different skills that you should know in this class. So here are reactions written for you, and it's told you that it won't work as it's written and why. And then how can we make it work? Okay, so I mean, when I encourage you to pause the video after I introduce the reaction so you can think about it first. Okay, because if you just watch me solve it, that won't help you to learn the material. So pause the video and think about why it won't work, and consider, is it written well to be SN2, or is it written well to be SN1, or neither? Okay. So remember that we are starting all problems with that. So let's consider all the factors. We have our leaving group is primary. Our nucleophile is an OH, which is basically not a good nucleophile. Okay, so not a good nucleophile tells us SN1. Primary tells us SN2. And HMPA is a polar aprotic solvent, and that also points towards SN2. So basically we have a mismatch reaction in which some of our factors are supporting SN2 and one of them's favoring SN1. So how can we convert this to make it work? How can we make this SN2? Basically, to be SN2, we want a good nucleophile. How do we make this into a good nucleophile? And we basically add a charge to it. And so if I rewrite this reaction, we keep our bromide as is, and then we want a negative charge on our nucleophile, which means we'll have something like sodium. HMPA is still a good solvent, so now everything is pointing towards SN2. We have a primary leaving group, a good nucleophile, and polar aprotic solvent. So this should be a nice clean SN2 where this displaces here. This is the nucleophilic atom is going to be attached where your leaving group is. So I would draw these carbons all the same. So those are my 5 carbons, and then instead of bromine being attached here, my nucleophile is going to be attached. And so that will allow me to get that product. And then in my case, we're going to have sodium bromide and not HBr. So I guess that's different from the reaction above, but we're still getting the desired product, which is what the problem's asking us. Alright, so in this next question, we're asked, what is the best way to make the product shown with the correct stereochemistry? Okay, so we're kind of working backwards in this case, and working backwards is called retrosynthesis. Basically, what substrate plus what nucleophile will allow us to get that product, and it has to be R. So if we're starting from scratch and we want to draw R, usually what I do is I just guess that it might be a wedge, and I assign R, S, and C if it works. So this is 1, 2, 3. If I make my circle as is, lowest priorities in back, it's actually S, and so I guessed wrong, which is fine. I'm just going to switch it to be the other, which is back. And so 1, 2, 3. It looks like S, but because the lowest priority is coming towards us, it's R. Okay. So this is R2-pentane thiol, and we're asked what is the best way to make it. Keep in mind that you know SN1 and SN2, and we had learned that SN2 is the best way to make just one stereocenter. And so we really want to have a SN2 reaction. And so we have our carbon backbone, and our leaving group has to be attached where our nucleophile is now attached, and we need to introduce our nucleophile. So what nucleophile will give SH? Basically, we sh minus, so we can add something like NaSH, for example, or lithium, LiSH. Or you could even put SH minus, and that would be fine. We want a polar aprotic solvent, so pick one of the four. And we want our leaving group attached at this carbon here. And do we want it front or back? So if our product has it back, that means our leaving group must have been in the front. And so when this did a SN2, it did an inversion to give that product. So we work backwards, looking at what our nucleophile had to be and whether our leaving group was front or back to give the correct stereochemistry. So basically, we had to start with S2-bromo because of our numbering scheme. So S2-bromo pentane plus sodium thiol or thiolate, either one, would allow us to get R2-pentane thiol as a product. Okay, so retrosynthesis is kind of working backwards using the same skill set but in a different way of thinking. And this last one is one other way of thinking. So we're given the starting material and we're given the product, and we need to determine the reagents. So again, we still want to identify SN1 versus SN2. Okay, so first we see that we start with R and we end with S, and so we want to do an inversion. To do an inversion, we want to think SN2. This must be our leaving group because it leaves and is gone. It's one of the complicated leaving groups that we're not really exposed to as much, but it is on your leaving group chart that's on your slide. And then this is our nucleophile. And our nucleophile is N3, and we did learn that in our nucleophile, that we introduced that with N3 minus. And so when we look through these, basically what we're doing is we either rule out ones we don't want or include the ones we do. And so if you look, all have N3 in them. This has an I with it, I N3. We've never learned anything like that. These have methanol, which is basically CH3OH. And then we have HN3 or NaN3. Okay, and so that's the difference between them. And then here we have DMF. So what's changing is the nucleophile and the solvent. And in these two cases, our solvent is polar protic. In our last case, it's polar aprotic. So which set of conditions do we want for SN2? We want a good nucleophile, so NaN3, which is the same as saying N3 minus, and we want polar aprotic. So this is a mismatch case and not good. We have a good nucleophile but a bad solvent. And here we have a poor nucleophile. We don't want an H on there because it makes it neutral. Remember, we prefer the negative charge. And it's a poor solvent. So these are bad in both cases, and this one would be favored. Okay. So I encourage you to do a lot of SN1 and SN2 practice in a lot of different ways to make sure you really learn these concepts. When you're looking at the sapling problems, you'll see that some directly get at the rate as well. And so these problems didn't really deal with rate. But keep in mind, for rate of SN2 and SN1, the fastest rate for SN1 is a tertiary leaving group is better than secondary. For SN2 for rate, we would rather have a primary leaving group over secondary. We want a good nucleophile, and we want a poor nucleophile. And we want the most nucleophile we can, so a high concentration of nucleophile. And we want polar aprotic solvent. And this one would be polar protic. And how can we increase SN1? We can increase the rate, remember, by adding heat. Heat will speed up the reaction because it helps the leaving group to leave.